Hello, everyone. I want to welcome you to this week's FRC Workshop. We are so pleased that we have Ian here from IC Robotics, Team 5584. He's been doing FRC for a very long time. He's living down in Melbourne, so I hope you're safe down there with everybody. And you are here tonight to talk about motors and gearboxes. So I will turn it over to you, Ian, and we're all looking forward to hear what you have to say.
Oh, great. Thanks, Lauren. Thanks for the introduction. Yep, I'm going to be talking about gears and motors tonight. Just before we start, I think I'll just say this session is going to be recorded. So if at any point you're not keeping up with some of the maths, or you can rewind, obviously, or watch it at a later date multiple times. There's quite a lot of material we're going to go through tonight, and to fit it in time, I'm going to go through it reasonably quickly. The level that we're targeting is sort of first or second year teams. I would expect that veteran teams probably will know a lot of what's already in here. And the last thing I wanted to say is this is the approach that we use as a team to do our calculations for motors and gearboxes. I'm sure there are other ways. At the end of the presentation, I will provide you with a link to some online spreadsheets that are available, which do help you do a lot of the calculation within a spreadsheet. So as I say, there are multiple ways of going about it. Okay, so what are we going to do tonight? We're going to talk about motors, obviously. We're going to look at the range of motors that are allowed in FRC, and we'll work through in a three-step process to determine which motor will work for your particular task. There's obviously some maths. That's the M in STEM and STEAM. There's a little bit of science as well. A few physics expressions you may or may not have seen before. We're going to talk quite a bit about different gears. Your gear system is everything between the motor and what I call the final rotating part. So that may be belts, chains, tooth gears, and what we're looking for here, because there's so many different combinations, we're looking at what you might need to order, basically, because not everybody's going to have a full set of gears, belts, pulleys on the shelf. And then at the end, I'm going to finish up with the title of the presentation, which is whether we should stall or not stall. It can be a bit of a contentious issue, so I thought we'd cover that off at the end. Yeah, so hang in there. If there are questions, we'll probably keep them till the end. If you're watching this at a later date, when the YouTube session's closed, do please feel free to reach out to our team through our website, icrobotics.org. More than happy to support any questions or try and work through problems with you guys. Okay, so that's what we're going to be talking about. Why? I'm not sure how many people are online at the moment, but if there's anybody wants to prompt straight away on there or post something to the YouTube channel, just going to pause here for a couple of seconds just to see if there's anybody out there. Why do you think we need to talk about motors and gears? What are the different things that might be required? Why do we need to make a decision on this? I'm just going to pause for another 10 seconds. Okay. What I'll do now, there's a number of different reasons why we need to work out which motor we should use or how we should arrange our gearing. Basically, if you use a motor that's underpowered, it won't be able to lift the load that you're asking to quickly enough. You can use the weakest motor to complete a task, but at the end of the day, if you do use a weak motor, you're going to need a very high gear ratio, and it's going to do the job very, very slowly. So slow it may not even complete within your competition time. So that's a risk if you just go with an underpowered motor. It's very unlikely that you're going to have exactly the right gears you need on the shelf. There are literally thousands, if not tens of thousands, of combinations of gears, pulleys, chains, and sprockets. Even the most well-off teams won't have one of everything. That's that one. Maybe you just need to convince your team which parts to buy. This is another reason you can't just sort of say, I want one of these pulleys, I want one of those pulleys, I want a gear, I want a belt like this. You need to have something to support that so you can convince your team to spend some money on that. If we get it wrong, we might break something. Replacement parts can be expensive. They can have a long lead time, particularly in Australia. If you've ordered parts from overseas, they may take many weeks to arrive. Your build season is a limited length, so that's something to bring into question. Maybe on this top one, you've already had some experience in FRC and had motors that have overheated, or you may have even released some magic smoke. And that, for me, is probably the overriding reason. You really don't want to be at a competition and in this state where you've got, for whatever reason, parts of your motor are melting, and you end up with bad smells at the least, and sometimes smoke and flames coming out of your robot. This particular image here is in fact not a motor fault. It was a fault where the battery was shorting on the frame, but it serves to illustrate what can happen. And while we might have a bit of a laugh about that image now, at the time there would have been some very upset team members because at this point their robot's now out of the competition. Okay, so moving right along. Just give you a little bit of background. IC Robotics, we've been doing FRC for 5 years now. 2014 we did the DDU in Sydney. 2015 was our rookie year at the Sydney Regional. Prior to all of this, we were, it's a group of schoolboys came up with the Inventions Club. That goes way back to 2007. So that's where the IC comes from. So, yep, we're part of Team 5584. And there's a link to our website there. If you want to know more about the team or contact us, you can do that. There's details on the website there. This is me. Not going to stop on this particular slide for a long time. I've been a mentor with our FRC team since 2015. I studied electrical and electronic engineering in the UK and migrated to Australia in '98. Current role, I'm deploying software and system development tools, automatically deploying them for engineers across Australia. That's enough on that. Okay, a little bit of a nod here to some resources that we'll make use of during the call. We have a particular article called, there's a series called Behind the Lines on YouTube. They were all excellent. And there's one particular one that talks about motor selection and gearboxes. You may want to jump onto that at some point because a lot of the content that I've got here is based around that. The other two, there's 2 YouTube videos there. I only use one of those. It's a particularly poor quality in terms of the video quality, but the way it describes gears and ratios, I couldn't put something better together. So we will actually use that later on. So these are some of the sites that we'll be looking at. Okay, this presentation is obviously on YouTube and it's recorded. If you go to our website and search for motor selection, you'll see some material there already. I'm going to be uploading this presentation there. Everybody's welcome to reuse it as either through the YouTube video, you can view that, or also have access to the presentation material if you would like to reuse it. So that's our website. You'll see there's a search up in the top corner there. That's where if you type in motor selection and hit the go button, you should get through to this presentation. Okay, so where do we start? Let's look at the motors that we're allowed to use. If you've been in FRC for a while, you'll know that they're a restricted set, and specifically Rule 27 limits you to this set of motors. Now, while it's restricted, there's still plenty of options. We've got standard, what's it called, sim and bag motors. Every team will have at least one of these. These come with your rookie kit of parts. and every year you seem to get another couple of these. Good solid motors, very durable, and perhaps a little on the heavy side. You can also get a Venom sim, which is basically has an integrated motor controller on the back. That's what this is here. We've got a wide range of what I've called compact brush motors. There's motors, the two blue ones at the bottom from Bainbots. You've got your 775 Pro, and then a collection along the top that Andy Mark supply, including their Redline motor. They're all a similar sort of form factor, these motors. Some come with gears mounted on the spindle, some without. And you will, if you buy sometimes with an integrated gearbox, it'll have one of these motors on the back end. We've also got a group of motors here which come with an integrated gearbox. So you've got a snowblower here, which is actually, it doesn't drive the snowblower itself, but it drives the hood of that. That's where that's come from. Note that the new ones have a hex shaft in, which is much better and easier to integrate with than the previous spindle that used to just have flats. There's a Bosch seat motor. There's a collection of window motors. This one here is an older version. I'm not even sure it's available now. And on the right, we've got a tailgate motor. Again, all of these have some form of gearing built into them, and the motor is integrated with that. There's some special cases here. The Nevo-Rest motors, you have to use the gearboxes with those. You can buy the motors separately, but they only work with the classic and orbital gearboxes. And then there's another one, this Denso throttle motor. Every team will have some of these, maybe even a bag full. We've always struggled to integrate them electrically, and also the gear connection is a different pitch. So they're just a little bit hard to work with. There is a 3D printable gearbox for this motor. You might want to experiment with that in the off season. We've now got a range of brushless motors. I'll talk a little more later about the differences between brushed and brushless. These are two, the Nidec on the left and the Falcon 500 on the right. They both have integrated motor controllers. And then we've got, which were released, these Neos, I believe it was last year they were released. This is the bigger one, it's just a Rev Neo, and this is the Neo 550. So that's a little bit of an overview of the motors that you're allowed to use. I've mentioned there two different types of motor, or two categories. One's brushed and brushless. So I'll just do a little, there's a couple of really good animations on the VEX website I've just stolen. I've given them credit at the bottom there. This is a brushed motor configuration. It's called a brush because there's literally two carbon brushes that rest against this middle part, which is called the commutator. So as that motor rotates, it's actually doing the switching automatically, so that the windings, you've got electromagnets in the middle on a brush motor. You can see that as they pass a pole, they're switched off. As they're approaching, as they go past the pole, they change to the pole that they've just passed. So an electromagnet has a north and south, the same as a permanent magnet. So we've got permanent magnets on the outside of a brush motor, and all magnets work. South pole is attracted to a north pole, north to south, and they're repelled from themselves. So when you see, for instance here, this one goes blue, as it goes over the top, it's being repelled from the south pole and attracted to the north. And you see as it goes around, the direction of the current through the electromagnet changes direction. However, the supply is always in one direction. So you'll see there's always current is going in this direction. So that's a brushed motor. Brushless is this one here. Big difference is there's nothing touching or electrically connecting with the rotor in the middle. You can see that the rotor in the middle is the permanent magnet, and the electromagnets are on the outside. Now, as the poles go past each of the electromagnets, they go off, much the same as that. That was the same that happened in the brushed motor. And you can see that the attraction, the pole changes so that it attracts, for instance, this is a north pole, it's attracting south As that passes, it changes to, or it turns off, and now it turns on, and now this is a north to south pole attracting the north. So that's how it manages the rotation. Now, the complicated thing with this is you'll notice that if you look at the little red wires that are on each of these, the current flow changes direction. So on this one, it's going in, not going anywhere, and now it's coming out. So this means that you need a more advanced motor controller to manage the currents coming in and out of those three windings. So whereas with the brushed motor, this one, the switching was done automatically and mechanically between the brushes and the commutator. With this one, the switching is all done electronically in the motor controller itself. Okay, now there are two types of brushless motors that we have in FRC. One's called an in-runner, brushless DC motor, and the other's called an outrunner BLDC, brushless DC motor. The difference here is with the in-runner, it means the inside part with the permanent magnets is running around in circles. So examples of that are the Falcon 500, the Nidec, and also the Neo. They're all what are called in-runners. So if you were to hold the motor, the outer shell is stationary with all the windings to create the electromagnet, and the rotor in the middle is what's going around. Whereas an outrunner, the stator is in the middle. So what's actually happening with this particular motor is the case is the bit that rotates. Seems a bit weird to get your head around, but once you've seen one in operation, you'll understand what I mean. So again, the windings are stationary and the permanent magnets are the bits that are moving. And the key thing there with a brushless motor is that the windings, you don't have to connect across because they're not rotating in either of these. You've got a stationary connection, you don't need a commutator. What does this mean? Okay, brushed motors. Typically they're lower cost. The vast majority of the motors you're allowed to use with FRC are brushed motors. Brushless have only come along in the last 2 years, maybe 3 years. The Nidec was available. You can use the cheaper controllers, whereas with brushless you need more complexity in the controller and it's naturally more expensive. There's another couple of reasons there. Advantages for brush, less relevant to FRC. I'll just put them in for completeness. Brushless. Okay, so they operate effectively at all speeds. If not all speeds, they've got a wider band of speeds where they are much more efficient than a brushed motor. They're typically got a higher power density. That means they're able to produce more output power for the size of the motor. They're lighter quite often for the power that they put out. Something like the Falcon 500, I think, is less than, it's about 40% of the weight of a SIM, and it has a built-in motor controller. So because you don't have a commutator and brushes on a brushless motor, you've got lower electrical noise, and they're also, I'm not sure whether they're better thermal characteristics. Being smaller, the heat can get out quicker. Okay, so motor control wiring. Let's talk about that a little bit. There are two control systems. I know back in the video that Project Bucephalus did 5985 a few weeks back, they talked a bit about the PWN and CAN circuits. You can use one or both. Your robot can use a mixture. It can be all PWM or it can be all CAN. So with pulse width modulation, you've got this 3-wire. There's a black, red, and white go to each motor controller from the RoboRio. So this is what we'd call a star topology. You've got the RoboRio in the middle and separate dedicated line going out to each of your motor controllers. With CAN, that's slightly different, so significantly different. It's a digital messaging system. It was developed by Bosch, I think, back in the 1980s, targeting motor vehicle connection. It's increasingly part components of vehicles are becoming more complex. They needed a standard way for them to be able to talk to each other, so that's where it came from. Interestingly, the CAN network is now used even on the electronic gear changing on Shimano gear set on a bicycle also uses the CAN messaging system. This is different in the sense that it uses 2 wires, just green and yellow. It's in what they call a daisy chain configuration. So you have a yellow and a green coming out of your Robo Rio to your first motor controller, yellow and green to the next motor controller, and you could have a dozen or more of these if you really needed them. Eventually they end up with a yellow and green going to the port on the PDP. That's the typical configuration. Okay, motor controllers. So for every motor that you put onto your robot, you're going to need some sort of controller. There was a mention earlier with brushed motors. You can just use a simple relay or similar to turn your brushed motor on or off to a set voltage. You can't do that with brushless motors, and not many teams will do that. They'll typically use one motor controller for each motor that they've got on the robot. There's 15 motor controllers that are now allowed. Large list, and can be quite daunting. Some of them support PWM, some just can, others will support both. So what I've done here is put together a table. Oh yes, there's also some that are dedicated to specific motor type. There's 3 of them in fact. So there's the Talon FX motor controller you can only use with the Falcon 500. It's actually bolted onto it. The Nidec also has a built-in motor controller, and then the Venom will only work with Sims. So let's just move to these tables here. So what I've tried to do is try and give a bit of a visual comparison of what each of these different motor controllers on the left will provide for you. All of them provide PWM. Some of them also have support for CAN. Most will support brushed motors. There are some exceptions. This is a dedicated one to that motor, so it doesn't support brushed motors. It is itself a brushless motor. And where I've got non-specific on this side, some of the motor controllers are dedicated, so they are specific. This one, for example, is specific to that motor controller. Talon FX only works with the Falcon 500. And then you have some, this is the second bit of the table, again, so the Venom only works with the Sim, and none of these here work with brushless motors. Interestingly, going back to that first one, the Spark Max supports PWM, CAN, brushed, and brushless, and it's non-specific, so it's not tied. You don't have to use it just with the Rev Neo or the Rev Neo 550. It's very versatile. Okay, so choosing a motor. Typically, we are presented at the beginning of the season with some sort of problem. There'll be, well, it might be multiple problems that you've got to overcome, but one of them typically involves some sort of lifting. So that's what we're going to focus on here is a subsystem that has to do some sort of lifting. You can see in the one on the left, the robot had to lift itself off the ground and climb up a rope and stay there at the end of the game. That was 2017. In 2015, Recycle Rush, which was our rookie year, the robot needed to be able to lift and stack these totes, which are the grey or black boxes that you have your kit of parts delivered in. You also needed to be able to put a garbage bin on top and a pool noodle. So it was quite a unique challenge that year. So at some point we determined that motors are going to be used for the lifting bit of the challenge. You don't have to restrict yourself to motors, but it's nearly always you will end up using motors for the lifting part of the challenge. So basically what we're looking for here is some way of choosing which motors are going to be capable of fulfilling the task that you're expecting of it. We've devised a 3-step process for choosing a motor. So first thing we need to do is work out what you're planning to lift in terms of the mass or weight, how far you need to lift it, and how quickly you want to do that. So it's no good building a robot that can lift one tote on top of another and it takes 2.5 minutes. It's not going to be a robot. It's not going to be winning anything at that sort of speed. So that's what we mean by how quickly you want to do it. So for Recycle Rush, in our case, we had a sort of gantry system which held onto the totes and the bin, and that itself has a weight. The totes have a weight, so they were 3.5 kilos each. The bin, the garbage bin that went on the top was 3.9. So if we add all that together and we say that we need to be able to lift all of that lot, so that's 6 totes at 3.5, 3.9 for the bin, and another 10 for the gantry, which we haven't at the beginning of the season. We didn't know how much that was going to weigh. We knew if it was much more than 10, then we were probably going to bust our weight budget. So we just estimated that at 10. So 34.9 kilos is what we need to be able to lift. Now, maybe in your game strategy at the beginning of the season, you decided that you need to be able to lift this. You've got to be able to lift 5 and put them on top of another one, so you get a height of 6. So that sort of lift is about 0.5 of a meter for a tote, and we decided to add a little bit to that, so we had a bit of clearance when we were carrying them around. So we also decided that we would like to be able to do that lift in less than a second for us to be effective at competition. Some of these figures are, you might say, guesswork. It's true. I mean, the timing, you could say, well, 5 seconds, maybe that would be all right. Or we'd like to do it really fast. We want to do it in 0.1 of a second. I think it's wise to choose something that's realistic and reasonable. So we just went with the 1 second. Also keeps the math simple. Okay, so quick summary for step 1. We define what the lifting system needs to achieve. In this example, it's 34.9 kilograms, has to be lifted at a distance of 0.7 meters in 1 second. So what next? We can use some physics calculations to determine the work that needs to be done, and then from that we can work out the power of the motor, the power that's going to be expected of the motor to deliver that work in the time. So these 3 here are some basic physics expressions. If you haven't seen them at school yet, you will do in the near future, I'm sure. Basically, the work is a measure of energy, and it's the force times the distance. So the longer you move something, or the further you move it, the more work you're going to do. If you're trying to overcome a higher force, then you've got to do more work. Force is mass times acceleration. So the heavier something is, the bigger the force, and the acceleration, the more that there is, the higher the force that's going to be required to overcome it. Power is simply work, which is this here, the amount of work that you've done divided by time. So it's a rate of work, if you like. If we combine these equations, you can take the force equation here and put that into the work equation. That's what this first line is. And then power, as we know here, is simply work divided by time. So it's that divided by time. So that equation, we can now use, we can put our numbers into that because we know what the mass is. The 6 totes, the bin, and the gantry was 34.9 kilos. The acceleration, we're on planet Earth, so acceleration due to gravity is 9.81. That's fixed. And then the distance that we want to move it is 0.7 of a meter. And we're dividing that by the time that we want it lifted in, which is 1 second. So units are important here. You need to make sure that your weight is measured in, or mass is measured in kilograms, which it was. 9.81 is in meters per second squared. So that's another what they call SI unit. And 0.7 is a meter. So we could, if we'd have put 70 in there because we thought it was 70 centimeters, then obviously your result's going to be 100 times bigger, and we'd be looking at 23 kilowatts. We don't have any motors that can deliver that. So units are quite important here. Kilograms and meters here, seconds under there. Okay, so in summary for step 2, our lifting system needs a motor that can deliver at least 239.7 watts. Okay, step 3. Let's have a look at the motors and their power that they claim to be able to deliver an output. Now remember that we're looking for, it was around about 240 watts of power. There's a number of these motors. I haven't actually put all of them up here, but these are typical motors that you might have access to. So there's 4, 5, 6 there that you definitely can't use. They just don't produce enough power. They're not able to add enough power to be able to deliver your requirement. if you'd have come to this page and done all of your sums and you were looking for 1,000 watts because perhaps you'd chosen to try and lift in 0.1 of a second, you may have to go back and revisit your requirements, and so it's just not going to be practical to achieve it. So in this case, we need to get 240 watts. So we've narrowed down the number of motors down to 4. Okay, so the 4 are the Falcon 500, Neo, 775 Pro, and the Sim. All right, where do we get those maximum power data from? Well, every motor that's available, if you go to the supplier's website, it will be listed there. Conveniently, Vex Pro, I'm giving them a shout out here, have a website where they've pulled a lot of data together, not only for the motors that they sell, but also motors that other suppliers sell. And this column here is the maximum power output. There are some motors that aren't on that site, so you will have to go and download the data sheet or go to the website. For instance, the Rev Robotics Neo 550 isn't in that list. Neither is the Nidec brushless motor, so you will have to do a bit of rummaging around. Okay, has anybody noticed that some of the motors can actually deliver more power than the PDP? There's been a bit of conversation about that, particularly in the last 12 months with the release of the Falcon 500 and the Neo. Can deliver, both of these can deliver more than the theoretical maximum that you can put through the PDP. So the PDP is the power distribution panel, and it has breakers on it, and the maximum they can be are 40 amps. So if you've got 40 amps at 12 volts, you're only going to get 480 watts out of that before it starts tripping, or are you? Okay, here's a little quick look at the snap action circuit breaker data sheet. The snap action circuit breakers are the ones that we put into the PDP, and the biggest one of those we're allowed is the 40 amp one. So interestingly, if you look at this graph, you can see that it will deliver 40% almost indefinitely. Certainly it will deliver 100%, so that would be 40 amps for a 40 amp breaker. It will do that indefinitely, certainly throughout your whole match. But if you go above, say 150%, you can see that it will trip out in somewhere between 3.9 and 47 seconds. That sounds like a big range, and it is. But it basically tells you that if you're going to operate your motors well above, even say 50% above, which is what the Falcon would do if you run it at maximum power, 50% above what the circuit breaker is set for, it will actually trip out after somewhere between 4 and 47 seconds. So I probably wouldn't want to be relying on running those motors at full power. So this is what it'd be worth bearing in mind. And I'm saying this, we don't have a huge amount of experience with the Neos. We have no experience with the Falcon 500s yet. So I can't speak from experience here, but you may find that if you run those motors for a prolonged period or repeatedly go above the breaker voltage, the breaker current, you may start seeing them trip out a bit. That may change in the future. There is a new control system planned for FRC 2022, and that may, I haven't seen mention of a new PDP or higher current breakers yet. Just be aware of that. Okay, so getting back to our problem. We're lucky. We've actually got more than one motor that can potentially fulfill our needs, that will meet our requirements. Which one of those 4 do we choose? I just thought I'd pause here for a little while and see if anybody wants to post reasons why you might choose one of those motors above one of the others. And yeah, feel free to comment on the YouTube channel there. I'll just pause for say 10 seconds to see if anyone's going to post anything. No? Okay, well, what we'll do is I'll bring up this list. We'll talk through that. Okay, these are Some of them are technical, some of them are non-technical. At the end of the day, have you got any of those 4 motors in the workshop? You probably haven't got all 4 of the ones that we could use. You may only have one, you might not have any. So that may influence your decision as to which one you want to use. Space, is that an issue? If you're building this subsystem late in your build season, you might be short of space on the robot, so you may be forced to go for some of the higher powered, the brushless Falcon 500 perhaps, just because that's all you've got space for. Weight, is that a problem? So the difference in weight between some of these motors is 100%. So a Falcon 500 literally weighs it's about 40%, I think, of the weight of a sim. So, and it's more powerful. Funding, have you got an unlimited budget? Do you have any budget at all? If you don't have any, then you've basically got to use whatever you've got in your kit of parts. And lead time. This was particularly hard for us in 2015. Everything that we ordered needed to come from overseas, particularly with the motors. So your lead time, it can be an issue. So these are all sort of trade-offs, if you like. So we can do all the technical maths and decide what might be suitable. But at the end of the day, you need to be able to manage these things too. Okay. In our case, we were a rookie FRC team in 2015. We didn't have a huge amount of cash. We didn't have a lot of time. Weight, we deemed wasn't going to be an issue because we are only building one subsystem. By the end of the build season, weight was a problem, which is why our robot photos are full of holes, as you'll see later on. We had already been donated a drive base, and we had a few spare sim motors, so that seemed to be the logical choice to work with the sim. So that's why we honed in on that one. We actually had them on the shelf and we could get on with testing straight away. Okay, before we start looking at the gearing, so we've gone through a 3-stage process for motor selection. I just want to have a quick look at what are called the motor curves. Motor curves are motor specific. So the one that we're looking at here is for the sim motor. And what they do is they look confusing, and they're actually 4 graphs in one. So you've got 5 parameters there, so the speed, torque, current, power, and efficiency. And rather than having 4 separate graphs, you can actually overlay them all on one space, which is what's happened here. So if you like, if it's simpler, just think of the motor curves as 4 graphs in one. So if we looked at the speed, the blue, the speed versus torque. So you've got torque at the bottom. Speed is measured on the left-hand axis there, and it's the blue diagonal line that's going top left down here. Okay, so you could just use the graph with that axis, this axis, and that blue line, and ignore the other 3, and it would look like a normal sort of graph. We've put 4 graphs on top of each other. That's all there is to it. So motor curves are available from the supplier's website. Again, the VEX Motors page has a lot of data for the FRC motors. Not all of them, but it's a good place to start. Motor curves typically available in 2 flavors. One will have speed on the horizontal axis, which is what we have here. I beg your pardon, sorry. The second one has torque on the horizontal axis. So that's what we've got here. We'll have either torque or speed down here, and then the other 4 parameters will be here and here. In both cases, you'll see 2 curves for power and efficiency and 2 straight lines. Bit of advice, when you're looking at motor curve data, it's worth trying to hunt down the curves where the units for torque are in Newton meters or millinewton meters. If you look, you will find quite a few motor curves out there that have got torque measured in ounce inches or pound feet or kilogram meters. My advice is try and avoid using those. Pretty much all of the motors now the motor curves that you find now are measured in these proper units. So Newton meters or millinewton meters. If you find them with the other curves, you can get yourself knotted up trying to understand the conversions with ounces and pounds and feet and inches. Okay, so these are the 2 types of curves. And we've got one there with torque on the right, which is the one we were looking at before, with the other 4 parameters up the top here. And then we have a new, the second one is we have the speed on the bottom and torque, current, power, and efficiency on the vertical axis. And you can see they've both got 2 straight lines and 2 curves. In this case, this is your green one is the power curve. The red dashed one is the efficiency. The yellow one is for torque. And the blue one is for current. On this one over here, we've got 2 straight lines and 2 curves. So this purple one is current. The blue one is speed. Efficiency again is one of the curves, and power is one of the curves there. So they contain an awful lot of information, and they may look a bit confusing, but we're actually going to step through and use these when we're talking about the gearboxes to work out what the import torque is for our gear system. So we will come back to these and actually use them a couple of times. So I've just given you a little bit of an overview there. Okay, different gearing systems. Your gearing system is from the motor right through to what I call the last rotating part of your system. So that may include chains and sprockets, it might include belts and pulleys, or tooth gears. It could just be one of those. It could be 2 of them, it could be 3 of them. So in our case, we end up using all 3 of those in our tote lifting robot in 2015. So no, this is important. While you might not think of the last pulley or the last bit of movement isn't part of your gear system, it is. It's equivalent to putting smaller wheels on your bicycle. You're not changing anything to do with the chain or the sprockets. You're putting smaller wheels on your bike. You'll find you'll be able to climb steeper hills. That's because you've changed the gearing system overall, and you'll be able to find you can climb steeper hills, but it will be done slower. Similarly, if you reduce the diameter of your robot climber bobbin, it will increase the torque, so you'll be able to lift more but slower. So it's important to bear in mind that final part of the gear system, or the last rotating part, also contributes to your gear ratio. Okay, so let's move on to look at those different things. We mentioned belts, we mentioned chains and sprockets, and also gears. We'll go through each of those now. So chains and sprockets in FRC tend to be what are called either number 25 or number 35. So the first digits, so the 2 or the 3 refers to the pitch. So it's the number of eighths of an inch between the pins on the chain. So for a number 25 chain, this will be 2/8, which is a 1/4 inch, or 6.35 millimeters. For a number 35, it will be 3/8. So that will be 0.375 of an inch, or 9.5 millimeters. The last digit, which I only learned recently, actually refers to the type of the chain. So if it's a 0, it's a normal chain. 1 is a lightweight chain. 0 and 1 are what are called a roller bushing chain. And number 5 means it's roller-less. So that's just the type of chain. Okay, so useful sites. This is a really good website link for calculating the number of chain links that you need and the distance between centers. Why is the distance between centers so important? Well, if you're going to, any gearing system is going to need to rotate about a point. If you don't get the distance between the centers right, then you're going to have, in the case of a chain or a belt, a very slack or an over-tight situation where it doesn't work, it can bind or actually jump off. So it's important that you get that center distance correct. So for each of these different gear types, I'm going to talk about the center distance and how you might calculate that. In this case, this is a really useful website for calculating it. So if you had 2 sprockets, you're able to type in the small sprocket and the large sprocket size. You can put in an initial distance, and it will tell you how many links that you need, how long your chain needs to be. When you are building with a chain and sprocket system, try to make the number of links in the chain even. That's important because if you think about a chain, it actually consists of what are called inner links and outer links. So there's an inner link here and an outer link. So if you were to make it an odd number, then you have to put in place what's called a half-link connector, and they're not particularly reliable. So it's worth trying to organize your distance between centers so that your gears, so that the sprockets, the distance between the centers of the sprockets needs to be so that you've got an even number of chain lengths. Okay. Key things: if you choose a number 25 chain, use it with number 25 sprockets. It won't work with number 35 sprockets. So when you're ordering sprockets online, be mindful of which size chain you're going to be using. Chains do stretch over time, and that can be quite considerable in an FRC match scenario because it's early in its life. There's different ways you can manage that chain tensioning. You can use a chain tensioner. Some teams just replace their chains after each event. You can also buy pre-stretch chains. They're pre-loaded, so they won't stretch anymore. They basically had the initial stretch applied to them. Other teams will actually apply a small amount to the center distances so that when they first fit the chain, it's really quite tight. It's hard to get on. So in that situation, you might want to add 0.5 for a number 25 or 0.3 for a number 35 chain. That's just in an FRC scenario where your chain lengths aren't massive. Obviously, if you're in some sort of industry situation, then you're going to need to provide other amounts to those center distances. Okay, let's talk a little bit about belts. Belts in FRC tend to be 5mm pitch. So the pitch is the distance between the centers of the belt, and they're either 15mm wide or 9mm wide. So you'll need to, if you're buying belts and pulleys, you need to make sure that you're either 15 or 9mm belt and pulley. Obviously, you're not going to fit a 15mm pulley, a 15mm belt onto a 9mm pulley. The markings seem a little bit strange. So this particular belt has 4255M15 on it. That means the first 3 digits are for the perimeter in millimeters. So that's the length. If you were to lay a ruler around the outside of that, or tape measure so it bent round, you'd find that it's, for that particular belt, it's 425mm in circumference or perimeter. Pitch is the distance between the teeth. So that's what the 5M means in the middle of that number. And the width is 15mm. That's the last 2 digits of that code. So useful tip. Belts don't tend to be marked with the number of teeth, but you can easily calculate that because you know what the perimeter of this is. It's 425mm. If you divide that by 5 for each tooth, then you'll get, you'll find if you actually went around that belt, you'd find that there's 85 teeth. Okay, there's another useful site there for working out the center distance. So remember how I said one of the important things you need to be able to do is to work out the center distance so you're able to mount the pulleys so that your belt isn't too slack and you can actually get it on. So that's quite important to be able to work out the center distance. So this is that website. You can see you choose the type of belt. You'll put in the size of your first pulley, the size of your second pulley, and what you'd like a rough estimate of what you'd like the separation to be. You'll know that. You'll say, well, I know it can only be 30, maximum of 30 centimeters, or in this case, it needs to be in inches, unfortunately, but you'll know what that distance roughly wants to be. And as you type that in, it automatically calculates the belt that you would need and the center distance between your 2 pulleys. So it actually gives you 2 answers. It gives you the belt that's slightly smaller than what you would ideally have, and it gives you the one that's slightly bigger. You then have to choose because belts come in set sizes. So it only gives you the ones that are immediately close to what you would like, and you have to settle for one of those. So in this case, we were looking for a 4.42 center, and it's saying that you can either go back to a 4.34 or a 4.64. Okay, there's another reference here, which is the actual supplier's PDF. Talks a lot in detail about how belts should be used in an FRC or in a first first environment, it's quite a useful read. Okay. With belts, yes, if you don't have access to accurate manufacturing, so that means if you can't make your center points for your bearings accurately, then you need to either add an amount to the center distance to make sure you have your belts tight, otherwise they will jump. Alternatively, what more experienced teams tend to do is use what's called a backside idler, which is like a pulley resting on the outside surface of the, or pushing against the outside surface of the belt to make it tight. Or you can actually have what's called a sliding bearing block. Now, neither of those two solutions would I expect to see on a first or second year robot. So those are the things that you might want to look into if you're going to go to belts in an improved robot in your third year, maybe. Okay, let's talk a bit about gears. So toothed or spur, also called straight cut gears, are probably what you starts talking to you about gearboxes. Typical gears in FRC, if you look them up on the supplier's website, they'll have things like 20 dp or 32 dp or 48 dp. What does that mean? Well, dp is what's called the diametral pitch, and it actually relates the number of teeth to the pitch diameter of the gear. So if your N there in that little expression is the number of teeth in the gear, the pitch diameter is what tells you how close together the teeth are. So the diameter, the dp tells you how close the teeth are together, and the PD tells you about what's called this pitch diameter, which is the effective diameter of your gear. So it's important to get, if you're building gears that need to mesh, they must have the same dp. So you can't have a 20 dp gear meshing with a 32 dp gear. So think about that if you're ordering gears for a gearbox, they need to be the same dp. Okay, so to work out the distance between centers for gears, you simply halve the sum of the pitch diameter of the two gears. So for example, if we've got a sim motor with a 14 tooth 20 dp gear attached, say we want to mesh this with a 50 tooth 20 dp gear. Notice they're both 20 dp, so they will mesh together. What's the distance that we need between centers? Well, if we take the equation that we had before, which is number of teeth equals dp times pd, we can rearrange that and say that pd equals number of teeth divided by the diametral pitch. So in our case, we've got the dp in both equations is 20. The number of teeth is 14 and 50. So we've got 14 divided by 20, and 50 divided by 20 gives us 0.7 and 2.5. So that's the small gear pitch diameter. So to work out the distance between the centers, we simply add those two together and divide by 2. So 0.7 plus 2.5 divided by 2 is 1.6 inches. Okay, so I've explained all of that, but there are plenty of good online gear calculators available that will automatically calculate your separation distance. And the link I've put here is a how-to gears on the West Coast Products website. Well worth going and having a look at. Just as a matter of interest, you could check this yourself if you wanted to. If you look at the Tough Box Mini gearbox that comes with the rookie kit of parts, where the motor comes into the gearbox is here. The motor is fitted with a 14 tooth 20 dp gear. If you actually measure, if you put your sim motor in there and then measure from the center of the spindle of the motor across to the center of this first cluster, you'll find it's 1.6 inches. Interestingly, if you check the website for the Tough Box Mini, you'll find that all of the combinations for the second stage, which is this gear and this gear, they all add up to 64 teeth in total. So that means that the second stage cluster and the output gear are always going to be a set distance apart. They're always going to be this 64 divided by 20 divided by 2, which is 1.6 inches. So it's also 1.6 inches here. Why is that a good thing? Well, it means that you can use the same housing without having to put extra bearing holes in place to produce multiple. I think there's about 6 different gear ratios you can put in there in this Tough Box Mini, which is kind of neat. Interestingly, though, if you look at the CAD drawings for a Tough Box Mini, they actually have a separation here between where the motor spindle is and the first gear cluster of 1.603 inches and not 1.6 exactly. Why might that be? Well, it comes down to the fact that gears can't be made precisely. They're made within a certain tolerance, and to cope with this, you need to make sure that your gears don't bind. And binding is where they, if you've got 2 gears that are just slightly off center, the way they've been made, they may bind and not actually rotate freely. So this is where you add, in this case, 0.003 of an inch has been added. In millimeters, that's quite a small amount. It's 0.02 of a millimeter. And the recommendation is for single stage that you add about a 0.025 millimeters. And for multi-stage gearboxes, depending again how accurately you can actually produce your bearing plates, between 0.05 and 0.075 for a multi-stage gearbox. So that's all to prevent the binding gear ratios. Let's have a quick look at a video. I can't explain this better myself, so I certainly couldn't draw this as well as they put this together. We're going to look at some video that's got gears, 3 sizes of gears in it. The red gear is 12 teeth, yellow is 24, and blue is 36. So we'll quickly play this. Okay, so here we've got very simple. Input gear is red, and what we're going to find out is it goes around 3 times for every time the right-hand gear goes around once. So that has a gear ratio of 3 to 1. We can introduce a 24 gear in the middle. We're now going to see that the left-hand gear is going to go around once. The middle gear has only gone halfway around, and the large gear has only gone a third of the way around. So you've now got a 2 to 1 gear ratio on the left, and a 1.5 to 1 ratio between the between the yellow and blue gears. So you'll see the way that this now works is that we multiply those 2 together. So 2 times 1.5 gives you a gear ratio of 3 to 1. It means that the left-hand gear is going around 3 times for every rotation of the right-hand gear. Okay, so let's go back to our 3 to 1. What if we wanted a much bigger gear ratio? Clearly, we could just have an even bigger gear on the right, and we'd then produce a higher gear ratio, but that's going to get very clumsy and very big very quickly. And if your robot is being driven on along the ground, you can't have a massive gear right behind the axle, so you're limited with how big your gears can get. And this is why we introduced what are called compound gears. And if you look back at your Tough Box Mini, this is exactly what that looks like. It's got a red drive on the left, which is driving the first cluster gear, which is the yellow one. That's got a gear ratio of 2 to 1 in this case. And we've also got this second stage, which is a 3 to 1. Now, if you put those together and bind and lock the 2 middle gears together so that they rotate at the same rate, then you've now got what's called a compound gear train. So what we'll see here, hopefully it will start up. There we go. So this is a 2 to 1 in the first stage, and a 3 to 1 in the second stage. You now multiply those together to get a 6 to 1 gearbox. So 6 to 1 means the left-hand gear is going around 6 times for 1 rotation of the right gear. I'm hoping that that's what they've got. 2 times, a 2 to 1 and a 3 to 1 gives you a 6 to 1. There we go. I think there's also an example where they introduce, I think there's another couple of examples here. That's actually going to count through, so that should get up to 6. While the right-hand wheel gear does just 1 rotation. So yeah, that's demonstrating that it's a 6-to-1. So in the next one, we'll see that the middle gear, they're going to make even bigger. There we go. So you've now got 2 3-to-1. So your first stage is a 3-to-1, and the second stage is also 3-to-1. So guess what? Your overall gear ratio here is 3 times 3, which is 9. So that's a 9-to-1 gearbox. And here's another one. We've got a 1-to-2 on the left. This is actually a 3-stage. We've got a 3-to-1 in the middle and a 3-to-1 on the end. So that's going to have a total gear ratio of 2 times 3 times 3, which I think is 18. Yeah, there we go. So there we go, a little video. Hopefully that explained how gear ratios work. Choosing gears. Okay. We've had a different look at the different types of gear systems. We've worked out the distance between centers for the different gear solutions, and we've talked about gear ratios. Let's have a look at our real challenge to see how we worked out the gear ratio that would be required and what gears we needed to buy. So this is a picture of our robot. It's a bit difficult to see that there is actually there's a pulley mechanism across the bottom here and then a vertical pulley behind here. We had under the covers here, we had a 2-stage Toughbox Mini and one stage of chain driving from the output of the Toughbox Mini to a common axle that ran across here and drove the 2 belts that you can see at the bottom here. If I draw a little diagram side on, this is what we had. So we have a motor spindle here, Toughbox Mini with this 2-stage in here. We then had a sprocket and chain, 2 sprockets and a chain as the 3rd stage. 4th stage was a belt and pulleys, and the 5th stage was belt and pulleys. So that's the 5 stages that we had. Now recall earlier that we said the gear system is everything between the motor, which is that little point there, and the final rotating part. In our case, the 60mm pulley up here, that's what I call the final rotating part. From that point onwards, it's a linear motion that we're lifting our totes. So just to zoom in a bit on that top section, we've got a 60mm diameter pulley. It's lifting the load vertically. The load was attached onto the gantry was attached at this point. So the gantry, 10 kilograms, the 6 totes sitting in the gantry, and the garbage bin on top, all of that added together equal to 39.4 kilograms that we're trying to lift. And the force that we're trying to overcome is the force of gravity, which on planet Earth is 9.81 meters per second squared. So we're going to use those 3 figures in a minute when we start looking at the gear steps. So we've provided a 1 to 3 steps for your motor selection. We're now going to use steps 4 to 6 to determine the gears that we're going to use. At the end of this exercise, so once we've done all 6 steps, we'll know what parts we need to order if we don't have them on the shelf. So step 4, we're going to need to work out the torque of the motor shaft and the torque at the output of your gear system. So let's start with the gearbox output torque. So this is right at the end of our little diagram here. So at this point here, what is the torque required at the output of our gearing system? This is our final rotating part, and that's what we need to determine is the torque at that point. Now, torque is force times distance. Force is mass times acceleration. So the torque at the output is mass times acceleration times distance. Mass, we worked out, 34.9 kilograms. Acceleration due to gravity on Earth is 9.81 meters per second squared. And your distance, you have to be very careful here, the distance is the radius. So if we go back and have a look at this, here, this is a 60mm diameter pulley. So the radius is 30 millimeters. So between the center and the edge of the pulley is 30 millimeters. 30 millimeters is 0.03 of a meter. So remember your units when you're doing maths, you try and keep it in standard units, or what they call SI units. So we've got kilograms, meters per second squared, and meters. If we put millimeters in here, then you're going to end up with a huge torque over here of 1,027 Newton meters, and we don't have any motors that are going to be able to deliver that. So this is the output torque required for our gear system. Where did those numbers come from? I'll just walk through that actually. So 34.9 was the weight of the totes, the gantry, and the bin. Acceleration due to gravity, and 0.3 meters is the radius of the pulley. Okay, let's have a look at the input torque. So the input torque for the gear system is actually the same as the output torque for the motor, because that's where they're connected. So we can use either of those curves. We can use either the one with speed at the bottom or torque at the bottom. Let's have a look at the one with torque on the bottom first. Now, we worked out that we needed a motor to be running at 239.7, let's call it 240 watts. So I'll put a little orange circle there. First thing we do is we draw a line across, horizontal line, to where that intercepts the power. So we've gone from the green axis here, power in watts, and we hit the power curve here. We then draw a vertical line up and down so it intersects all the other lines and the axis down here. So what we've got here, 1.9 Newton meters. Okay. Let's have a quick check of the other figures and see what we're setting up here. Okay, so where this vertical line crosses the blue speed line, we can read off over here the RPM that the motor will be running at in this configuration. So it's just a little over 1,000. So that would be 1,200, so say 1,100 RPM. We'll go back this way from that point. So we're now looking at the red line. So efficiency here is where this orange line crosses the red efficiency line. We go to the right, we can see, ooh, that doesn't look so good. That's a pretty low efficiency. Anyway, let's keep going. What have we set up here? We've actually, if we run from this point here, we're going to be using a very, very high current. So it's going to be 110 amps. This is not right. Something's gone wrong. What's gone wrong is that we've actually chosen, if you come across from the power line here across, there is actually another point where the power curve is at 240 watts. So let's take a look at that. Let's start again. Let's come from power. Come all the way across to this point here. See, it's still the power curve. We then put in our vertical. We come down here, 0.5 Newton meter. That sounds more reasonable. We're going to be at a higher RPM, so around 4,200. Efficiency, so where that orange line crosses the red line, we come across and read off the red axis, 65%, 62, 53%. That's good. That's good efficiency. If you look at the efficiency curve, it only gets to about 65 anyway, so that's pretty good efficiency. And the last thing we'll check is the current. So where we cross the current graph line, we come across, which is purple, to here. And current in amps is 30. That's good. If it's less than 40, we can deliver that because the PDP, we can put a breaker in at 40 amps and we know we're in range. So remember the 0.5 Newton meters, that's important. And we'll use that in a minute to apply with our, that was the import torque, remember. Okay, let's quickly work through the other type of curve just to demonstrate that you can get the same answer from this curve where we've got speed on the x-axis. So here again, we look at the power of 240 watts. We draw a horizontal line across. We'll be a little bit smarter this time. We'll come right across to where we can see that the efficiency is high. So we'll choose this point on the green curve, not this one. We draw the vertical line down, going through all of the other curves, and then you can read off from there where we fit the yellow line, which is the torque in Newton meters, 0.5. We can measure off the efficiency from where we cross the red dash line. It's a little over 60%. And current is here, back over, I think we said before, it was about 30 amps, and that's what this curve's telling us. It's telling us exactly the same thing. So you can see, although the two curves are organized slightly differently, you can get the same answer again. 0.5 Newton meters is the key bit of information we want. So for step 4, the torque at the motor shaft, so that's the input to our gear system, will be this 0.5 Newton meters. And the output torque will be the 10.27. This is what we worked out earlier by looking at the pulley, the weight on the pulley, and the acceleration due to gravity. Okay, next. Step 5, we need to work out the overall speed ratio for the gear system. Now this is just an equation that is. You just have to accept this one. The torque at the input is equal to the torque at the output, multiplied by the gear ratio, divided by what's called the single stage efficiency, transmission efficiency, multiplied to the power of the number of stages in the transmission. This is probably a harder equation to get your head around. So what we'll do is we will just put our numbers into that and see where we go. So a quick word on efficiency. It is different for the different types of technology, between 93 and 98%, depending on the technology you're using. We're going to assume that it's 95%, so we're going to use a value for n of 0.95 for all of our stages, just to keep the maths a little bit simpler. So we can rearrange that last equation. We can divide both sides by T0, give us this one. We can then multiply both sides by n to the power s, which gives us this equation. And then we can just reverse it so that E is equal to E is our speed ratio for our gear system, for the whole system, which is a factor of the efficiency to the power of the number of stages, multiplied by the input torque, which we've already worked out, divided by the output torque. We can actually put our numbers into that now, because we know what our efficiency is. This is the 95% or 0.95. We've got 5 stages. So there are 2 in the Tough Box Mini. We've got the 1 sprocket stage, and then we have 2 stages of belts and pulleys. Let's multiply that by the TI, which is the input torque, and divide it by TO, which is the output torque here. Now, if you do all of that, put that into your calculator, you'll get 0.038. That doesn't look like a gear ratio. Well, the reason it doesn't look like a gear ratio is we normally write our gear ratios like this, which is 1 divided by the transmission the speed ratio, which ends up, if you take 1 divided by 0.038, you end up with a 26:1 gear ratio. So that's what we're looking for that's the total gear ratio from the pulley, or the motor, right the way through to the pulley, the final rotating part. Okay, so in summary, we need a speed ratio of 0.038, or 26:1. Now, we've got in the Tough Box Mini that we had in our kit of parts, there were 2 stages of gearbox already there. The belts and pulleys were all available to us through one of our sponsors, and provided we went with the 60mm pulleys, we got them at a very good price. So, if you like, some of the stages were pre-dictated to us, but there was one that we had a little bit more choice in, and that was the chain and sprocket stage in the middle. So let's work out the bits of the gear ratio that we do know. In the Tough Box Mini, we had 14-tooth gear on the motor shaft. That's driving a 50-tooth driven gear on the first cluster. Stage 2 was a 16-tooth to 48-tooth on the output cluster. As I mentioned, our sponsor was able to readily provide us with 60mm diameter 20-tooth pulleys off the shelf. So we use these 20-tooth pulleys throughout stages 4 and 5. So we know stage 1 stage 2, stage 4, and stage 5. The speed ratio is simply the number of teeth on the driving gear divided by the number of teeth on the driven gear. So if you take 14 divided by 50, you get 0.28. The second stage, also in the tough box, is 0.33. And our speed ratio for the last two stages, they're 1-to-1, because we've got the same number of teeth on the pulleys at each end. They're both 20-to-20, so your speed ratio there is 1, and your speed ratio here is 1. You might say, why do we need to bother putting them in? Well, the reason we should put them in, particularly because we're adding another 2 stages, you've got 2 more stages of inefficiency. It's only a little bit, you lose 5% with each stage, but it's important that we put that in there. So how then do we calculate E3? We know 1, 2, and 4, and 5. E3 for our chain and sprocket. What size sprocket do we need to go and buy? That's what we need to work out. Okay, so if you remember in the video that we saw earlier, for any gear train, you can just multiply the ratio of all the stages to get your overall ratio. So in our case, if we multiply E1 by E2, by E3, by E4, by E5, it gives us our total gearbox or gear system ratio. Now we know what E needs to be. It actually needs to be this 0.038. If you remember in step 4, we worked out that the overall gear ratio for our gear system, so we know that's 0.038. We know for our first and second stages in the Tough Box Mini that we're looking at 0.28 and 0.33. And for stages 4 and 5, we're looking at a speed ratio of 1 and 1. So we've now got an equation with all numbers except for one unknown. We can reorganize that. We can take the 0.038, divide it by 0.28, divide it by 0.33, and we can end up with an E3 of 0.41. So we now know that we've got to buy sprockets to go with our chain that will give us a 0.41 gear ratio for our third stage. So 0.41, again, that looks like 1 divided by 0.41 or 2.44 to 1. So that means for every time the input sprocket, which is on the side of our Tough Box Mini, goes around, needs to go around 2.5 times for every once on the larger sprocket that we're going to put onto the common axle driving the pulleys. What do we order? Well, you can't get exactly a 2.44 drive ratio, it turns out. You have to go with something close. Now, if you look at the smallest sprocket, the smallest one we could find that mated with the 1/2-inch hex output from our Tough Box Mini was available at Andy Mark, and it was a 16-tooth, number 25. The largest sprocket has got to be, remember the 0.41 for this stage was our ratio. So if we take 16 divided by 0.41, we need at least a sprocket of size with 39 teeth on it to get the gear ratio that we need. Andy Mark have got quite a range, so we could have chosen anything from 40 upwards. They all have the same bolt circle, so there's no issue with mounting them to the key hub, which is what we were going to use to mount the sprocket to the common axle. We actually went for the 60-tooth. We only really had one opportunity to order, so we went and we introduced what we call a safety factor here. We didn't know it was called a safety factor back then, but that is what it is. We knew we needed at least a 39 tooth on that larger sprocket, and we decided to go with the larger one, or the largest that we could get at that point, with a view to giving us a little bit of headroom. So we'll talk a little bit more about safety factors later. Okay, I just wanted to quickly whistle through a few of the off-the-shelf gearboxes that are available. I won't talk a lot about these, but certainly as a first or second year team, you would be looking at buying these sorts of gearboxes. You wouldn't be building your own gearboxes. They're nearly all compound gears. Things, the Tough Box Mini is what comes on your kit of parts. This one from Andy Mark takes two 775 motors, and the output shaft is identical, and the mounting on here is identical to a sim motor. So anywhere you put a sim motor, you can put this gear arrangement, much more powerful. There's a simple box. There's also a Vex Pro single speed, single reduction gearbox. So it's just got one ratio with three different options, but it's just a single stage. The one that we use an awful lot of, the Versaplanetary, this is a very versatile little gearbox. It actually comes apart. So these are, I forget what they call them now, but you can stack together these different gear ratios in here. You can have one, just one, which could be a 3-to-1, 4-to-1, 5-to-1, 7-to-1, 9-to-1, or 10-to-1. And if you have two stages, you can actually stack two of those. So you can actually get a large range of combinations from a 9-to-1 to 101, 100-to-1 gearbox. It also supports a lot of the motors that are available, and it does also have options. You can have a magnetic encoder section in here. There's a ratchet section, or you can even have a 90-degree drive, and there's a sim adapter required if you want to use it with a sim mode. Very versatile, compact gearbox. It does have some negatives. We'll talk about them later. But in terms of compactness and versatility, this is it's hard to beat, I would say. Okay, other gear configurations. Sometimes there's not enough space to put the motor where you want to put it. So you'll do things like have a series of stages of 1-to-1 gearing. It's exactly what we did on our 2015 robot. We needed to be able to have a lifting mechanism and a very thin part of the robot walls. So we used belts and pulleys to get the motion at that location, and the motor was buried way back in the back of the robot. Similarly, if you had a robot with a front intake, you probably don't want to put your motor right out at the front. So you'll probably have some 1-to-1 gears. You can have toothed gears or chain and sprockets, or even belt and pulleys. All of those could be in a 1-to-1 arrangement to keep your motor inboard, well away from other robots which are going to be bumping into you out the front. Bevel gearbox, we've never actually needed to use one of these, but again, if you can't get the motor to be in line and you need to mount it at 90 degrees to the rotation that you require, then you might consider something like this. All right, axles and shaft types. This can be a real headache. There's a variety of output shafts on motors, and also the axles that are used for various pulley systems. We tend to, as a team, try to home in and make everything half-inch hex. There are some of the earlier snowblower motors you'll find had these D or flat-sided spindles on their output. They're really quite awkward to reliably connect to. So it's much better to go for something with a common the hex or the 8mm round with the 2mm machine key. There's this new spline output. This is what the output of the Falcon 500 looks like. So I would suggest if you're going to, well, you will almost definitely be using sims, it's worth ordering a few extra of the machine keys. They do have a little bit of variance in them, so it's nice to have a few to play with if you're struggling to get a gear on. Just pick up a different one. You might find it slots on a lot easier. And they also get lost quite easily, so just have a spare bag of those around. Other good things to have. This is often an issue for a lot of new teams. They get in their kit of parts, they'll get motors that don't mate to the wheels or gears and things that they've also got. So a useful tip, if you can, before the build season starts, check your inventory and make sure that you can, every motor that you've got some mechanism for connecting it to gears or wheels. So make sure you've got, this is a steel spur that goes on the Falcon, so make sure that you can drive something. This is a useful adapter to go from a sim output to hex, and then all of your hubs can be simple hex hubs. Okay, safety factor. Yes, we talked about that. We mentioned it very briefly. So why do we need a safety factor? Well, safety factor is where we're not talking about the safety of people here. We're talking about putting in a little bit of contingency, because all the calculations that we do in maths and science for FRC, all the ones I've shown you anyway, they don't make any account for friction. So we're operating in this frictionless world, and that can be true if you think about the example we showed earlier where the robot is lifting in free space. It's not dragging against anything, so you could say that that's a perfect frictionless world. However, it's always best to have some safety factor. Don't always just buy the motor that just meets the power requirement. Always, or don't choose the gear selection that just meets your requirement. Always go a little bit further, even if it means your system will run a little slower because you've gone like we did with the gear for the recycle rush. We went with a significantly bigger gear, and meant that the motor could definitely lift, but it meant that we also lifted slightly slower than we'd originally planned. So safety factor, you'll find as you become more experienced, you can be a lot tighter with your safety factor. You can go nice and low. If it's mechanism that you've built before, and you're only using it in a controlled environment, say the end game where there's no other robots bumping into you, you're not dragging the bumpers along a wall or something like that where there's heavy friction. In those situations, you can go with a low safety factor. If you're a new team, if it's part of a subsystem that's going to get caught up with other robots or field structures, then you really ought to be looking at a higher safety factor. So don't just get the motor that just does the job. Get one that's 3 times more than you need it to do, because you are going to encounter these extra frictions that you've never seen before. Okay, so also you'll find some motors, we'll talk about stalling in a minute, some are more sensitive than others. That may be another reason to go with a slightly higher safety factor. If you're using some 775 Pros, they're a little bit more prone to overheating compared with the Sim, for example. Okay, so where do we apply it? Let's say in our example we had a power requirement of 330 watts, and you only have Sim motors. That's all we've got. That's all we had. So the maximum that they can deliver is 337 watts. That's not very much of a safety margin. So you might consider there's 3 different places we can look at applying the safety factor, and you only need to do it in one of these, not all of them. You could, at the beginning, you could say, well, is your team happy to apply the safety factor right back at the system requirements? So what if we said the lift took 2 seconds instead of 1? So that would get us a 2-second safety factor just using the motor that we've worked out already. Second option is, rather than changing that, you might say, well, let's double the output torque in step 4, or we could halve the required speed ratio. Again, you only do one of these things, and that gets you the, if you make that change there, then you'll end up with a system that has a decent overhead. At the motor itself, you could just put 2 motors into the torque box. So we had that as another contingency. The tough box, sorry, not torque box. The tough box mini has 2 inputs for motors. We could have put 2 Sims in. If we had the weight, we probably would have done that if we had the weight capacity. So there's various different places that you can apply your safety factor. Okay, motor and gearbox compatibility. Is it possible to break a gearbox? Yes, definitely is. Too much motor torque applied to high ratio gearbox may strip gears. Now this is particularly the case for the more versatile gearboxes, shall we say. So if you've got the very compact and the gears are smaller, they're finer, very fine teeth in there, you'll find, and the Versaplanetary is an example of this, with those types of gearboxes, you will find that they are very well documented. They have in their documentation, I think this for the Versaplanetary is a 40 or 50 page document that tells you about the load rating. So your load rating is really telling you what to avoid. So if we take a detailed look at this particular page in the Versaplanetary document. What you need to do is find the tables on the page that match your setup. So if you're going to use a Versaplanetary with a 1/2 inch hex output shaft with a two stages in the Versaplanetary, then you'll find with any of these motors, it'll support the first and second stage ratios in all scenarios. So you can go for the 775 Pro, you can go to 100:1. So that's a 10:1 and a 10:1. 10:1 first stage, a 10:1 second stage gets you 100:1. And it's green. So no matter what combination of stages you use, the 775 Pro or any of these, you're not going to break the gearbox. Step over to the right side, we're starting to use some slightly more powerful motors. So you're looking at your Sim, your Mini Sim, Neo, Falcon 500. There's some red cells there. You need to avoid configuring your gearbox with those. So if you set up your Mini Sim with a 10:1 first stage and a 7:1 second stage, there's a chance you'll actually shred the gearbox, you'll break it. So don't use that, okay? You can do a slightly lower overall gear ratio, or you can use a different motor, okay? So you can see as you go up with the most powerful motors that are on the market at the moment, or that we're allowed to use in FRC, your Neo and your Falcon 500, there's even more cases that you can't use. Okay, now for that, everything that I've covered so far, you can do through an online, oh sorry, this isn't an online page, this is actually a spreadsheet, an Excel spreadsheet that you download by a guy called John B. Nguyen. He's has this on his own website. It's also available via Chief Delphi. It doesn't have all of the motors in here. It hasn't been fully kept up to date, but you could adapt it to do that. It's an excellent tool. You can put in your gears, that your driving gears, driven gears, and it gives you the answers to a lot of what we've been doing by hand. Okay, and finally, I'll wrap up now. We've come up to our hour and a half. To stall or not to stall? That's the question we set ourselves right at the very beginning. First of all, what is stalling? Well, when you stall a motor, what you're doing is you're still putting power into the motor, but the motor's just not moving. It's not lifting what it's supposed to. It's jammed. There could be a multitude of reasons why it's not actually turning. It may just not be powerful enough. Either way, you're putting power into the motor. Now, power is a rate of energy transfer. So you're putting energy into your motor, and it's not doing anything. What's going to happen to it? It's going to get hot. All that energy that you're putting in, because it's not moving anything, it's not changing the potential energy of any other part. It's just sitting there, and it's converting all that energy you're putting in into heat. So should you do it? If that's what stalling is, should you ever do it? Well, if you were out in industry doing this sort of thing, you possibly wouldn't have a job for very long. So you should really avoid it. However, with FRC, you certainly can do it, and you can get away with it. We've managed to build systems which stall motors. If you only do it for a small period and you don't do it too frequently, you can get away with it. And that's what FRC is. You're not building a robot that's going to last and sit out on a chemical plant for 50 years and with no maintenance. You're building a robot that's got to run for 2.5 minutes. So why is it a problem? Well, all the power you're putting in when the motor's doing nothing is getting converted to heat. If you put enough heat into something, you're going to melt things. So the conductors inside the motor will start to short circuit. You'll release some magic smoke, some nasty smells, and you'll do some permanent motor damage. So we need some way of determining whether we can do it and how long for. So fortunately, the motors, most of the motors that we have for FRC, we can get data on what's called the locked rotor stall test. Now, what this gives you is an indication of how long you can stall the motor for before you're going to cause permanent damage to the motor. Now, remember, the important thing to remember, this is done at normal room temperature. So they've taken the motor, they've locked it, basically bolted its output shaft down, and then applied a level of power and seen what happens. Now you can see that if you say look at the green line on this chart, after about 40 seconds, this is for the sim, your motor starts to do something here. If we quit, this is at full power, so that's 12 volts. After about 40 seconds, it drops down here. Now, what's happening here is the motor's failing. That's something it's not going to recover from. So clearly, you don't want to stall at full power for that long. If we look at the other extreme, say here, we're applying 2 volts. You can apply 2 volts to a sim motor for 300 seconds or more. Now, an FRC round isn't 300 seconds long. It's 2.5 minutes. I forget what that is in seconds now, but you could certainly you could stall the motor for the whole match. You could stall it at 4 volts for the whole match, and you're not going to put it into any irrecoverable situation. Even here at 6 volts, you're going to get away with it. Okay, now that it's important to remember that these are at room temperature. So if you can't get your motor cooled down between your rounds, then you don't start over here. If your motor is already at an elevated temperature from the previous round, the time for it to reach point of failure will be closer. So that's important that you capture that. So if we look at the same sort of curve for a 775, so that one we were looking at was for a sim, big bulky motor, lots of thermal mass. If you look at a 775 Pro, it's got a cooling fan on the back, which only works while the motor is rotating. If you take that bit out of action by stalling the motor, you can see that it doesn't last very long. You're green again. If you're going to do it at full power, you get a couple of seconds. You have to drop right down to here, 4 volts, really, before you get a motor that you can stall throughout the match. So be very careful with the 775s if you're going to stall them. Any of the high power, lightweight motors, they don't have a lot of thermal mass to be able to cope with stalling. Okay, so when can you stall it? Well, if you only need low power to hold your elevator, if there's a lot of sort of back pressure, for want of a better word, on the gearing that you've got for your elevator, sometimes you only actually need a small voltage, 2, 4 volts, and you can hold it, and it will work. You'll get away with it. The motor will degrade over. You might not get 2 or 3 years out of it. You don't need 2 or 3 years. You only need the thing to last through a couple of dozen matches, and that is your season. So importantly, there needs to be adequate time between tests, matches, for the motor to completely cool. Because if it doesn't, then you're gradually accumulating heat in the motor in each round. So what you'll find is these curves only apply. The curves that have been measured, it's been done in a very controlled environment where the motor starts at what's called ambient temperature or room temperature. So you need to, for those curves to apply, you need to have a decent cooling off period between each of your robot uses. And that you may get that in a match. If you think that the time between qualification rounds can often be half an hour, that's good. However, what will happen, if it hasn't happened in your workshop, because in workshop you're often testing for a 4-hour stint, that's when you're really going to notice your motors are going to get warm. And that same thing can happen during finals. If you're in the finals, your rounds are much closer together. So what you will find is the magic smoke is much more likely in the workshop and during finals. Okay, what can I do to avoid stalling? Now we've only ever used ratchets. It is possible to use other mechanisms. So what do I mean by ratchets? Ratchets can literally be a stage in your versaplanetary, like this one. It's a little bit difficult to see. we've done this before. This isn't our robot. Other teams have done it. You literally put a ratchet spanner on the end of your spindle. You can buy, adapt, or even build your own ratchets. Here, some teams, I've never actually seen one in the flesh. I had to look around for some photos. But here, if this looks like a bike wheel disc brake, that's exactly what it is. And the same here. And they're using a pneumatic actuator. So you can't use the hydraulic disc brakes. They're not allowed in FRC because of the fluid, but you can get mechanical disc brakes. So you can adapt those, usually with a piston, to actually activate the brake. And the other option is constant force springs. So these are like an anti-gravity device, if you like. So as your elevator goes down, it pulls down this constant force spring, which when you actually, as the motor drives it up, it now isn't working on its own against gravity. It's got a spring that's trying to retract and pull it up. Okay, so I think that pretty much summarizes what I was going to say tonight. I've gone a little bit on longer than I was planning, but there was quite a bit of information in there. What I would like to do is hand back to Luan. If anybody wants to get in contact with us, feel free to contact us through the website. Facebook is also an option. And yeah, we'd like to be able to help people out.
Thanks, Ian. That was awesome. We have a couple of questions for you.
Okay.
So the first question is, do you have any recommendations for selecting a motor controller?
Yeah, okay. Probably the first thing I would suggest is you choose one type and stick with it until you have to. Don't have an inventory where you've got one of all the different types. We, for quite a while, used the Talon SRXs. They're quite robust. They only support brushed motors. But we have recently diversified a bit. We've gone to the Victor SPXs. They're a little bit lighter, they're a little bit cheaper, and we weren't using all the features that you get with the Talon SRX. Another one you can't really look past is the Rev to the Spark Max. That supports brush motors and non-brush motors, quite versatile. It's nearly the same weight as a Talon SRX, but it's actually it's probably got more going for it, I think, in its adaptability. It does have a bit of an awkward connector. The connector that goes to the encoder is a little JST connector, which I think we might have some reliability issues around that. Yeah, so that's probably where I'd be heading. Obviously, if you're going to get a motor, if you're going to go with the motors with dedicated or built-in motor controllers like the Falcon 500, you don't have a choice. I don't know, were there any other questions, Diane, from people online at all?
There's a couple more questions. There's also someone is sending you some applause in the chat. So I think people have really enjoyed your talk. Another question that came in is, do brushless motors have locked rotor curves?
Some do, yes. The Rev Robotics for their Neo, I've seen equivalent curves for those. I haven't seen them for the other two, so the Nidec or Falcon 500. Brush motors are a little different in that they've got built-in encoders, and they also have, all of them, I believe, have current limiting mechanisms. So when you do look at those locked rotor curves, if you go to the Rev Robotics website and search for the Rev Neo, you'll find that there is a link on there which takes you to the locked rotor curves. And they've actually got 4 sets. So there's a curve for 80 amp current limit, one for 60, 40, and 20, I think. And it gives you, where you see the torque drop right down. That's when you're starting to do damage. So they do actually exist. But hopefully we're going to get something like that for the Falcon 500s as well at some point.
Excellent. And I really like this question. It's a little bit more personal. Has IC Robotics ever managed to generate some of that magic smoke we all know about?
Not on camera, no. Yes, we have. There are a number of different ways. There's lots of different ways of generating magic smoke, and we've probably tried them all. Only in the workshop, fortunately, we've not been embarrassed. We haven't embarrassed ourselves in public. But there are quite a few different ways you can actually cause magic smoke. What we're talking about with magic smoke is where you're stalling the motor for too long and you're melting the wires. That can happen for a few different reasons. I'm just trying to think of the ways that we did it. A common way for us, we've done it a couple of times, is where if you have two motors on a common mechanical gearbox and somehow you're powering one of the motors and not the other one, or you're powering them in opposite direction, that has the effect of stalling. That's exactly what it's doing to the powered one. And that can happen, as we now know, in multiple different ways. It can happen due to one of the cables falling off of one of those two motors. So top tip here would be, if you have two motors with a common gearbox, make sure that you cable tie all of your connectors or glue them together so that they definitely aren't going to fall apart. That's been one of our magic smoke moments. Another one, we managed to drop a piece of swarf into, so that's like a metal filing, into the Robo Rio, and it shorted for one of our motors on our 2017 climber. It was shorting out the PWM signal to 5 volts. It was basically, it was trying to power, no matter what input signal we were putting in, one of the motors was always being driven at 100%. So needless to say, that one vaporized at one point. So yeah, there's a couple of different ways. I'm aware that with the Rev Robotics Spark Max motor controller, the Neo, or any of the brushed motors for that matter, if you connect them directly to a battery, we haven't done this yet, don't do that with a brushless motor. Basically, it will damage the motor and you will end up with smoke. So yeah, I think that's probably most of the different ways you can do it. But I haven't mentioned software. Of course, it's very easy in software to configure your motors to drive in the wrong direction. If they're in a common axle or a common gearbox that they're feeding into, you must make sure you're driving them both in the same direction. That would be it, I think.
All right, well, thank you so much. I think those are all the questions we have right now. I think this is a great resource that I think teams are going to watch over and over and over again. So much information and really, really useful information. I do have a little bit of breaking news because I think that there are a number of FTC teams who are watching tonight as well. We are going to have a virtual FTC kickoff this year. So be looking for information about that coming out soon. It's going to be on September the 13th, which is a Sunday in Australia, at 1:30 p.m. So we're pretty excited. We're going to have some teams from the Adelaide area presenting for that particular workshop. If there's nothing else, I just wanted to say thank you so much to Ian. This was great. I also want to say thank you to the people who work behind the scenes here as usual. We have Sarah from IC Robotics tonight, who's been assisting Ian down in Melbourne. And Gordon has been managing the chat and all of the other things that go on behind the scenes. So thank you so much to all of you. Any closing words, Ian?
Yeah, I'd just like to thank you guys for setting this all up. Yourself, Gordon, and Andrew have put in a good amount of time for getting these talks to run. Thanks for doing that on everybody's behalf. Yeah,
and don't forget Lyndall from Project Bucephalus as well. She's been there helping out all the time too. So, well, thank you everyone. I hope you have a great night. Stay safe, and we'll catch you all next week. Bye.